Linear programming is a strategy for dealing with problems involving optimization. Optimization problems involve the notion of maximizing profit or minimizing cost or something like that. Now, the variable that we are trying to maximize or minimize is found in a function called the objective function. And for our demonstration here, the objective function is this. And we're trying to maximize or minimize the value for z. Now notice z is written in terms of x and y. And we have involved with this idea a list of constraints that are in the form of inequalities. Now these constraints are actually constraining or limitations on the values that x and y can take on. All right, and so we have a list of inequalities involving x and y. Now here's how we deal with it. And I'm just going to go through the whole concept of solution here and then we'll look at it at an example and it'll become much more clear, I'm sure, at that point. Okay, so we have an objective function, we have a list of constraints in the form of a system of inequalities. So we solve the system of inequalities and we find a region in which x and y values can fall for our objective function. Now, I have constructed the graph of these four inequalities, and this turns out to be the solution region. Now, I have cleaned up the graph quite a bit. You know, this little segment right here was part of a longer line, and the solution region for that line was on this side of the line. And for this line, it was on that side, and for this line, it was below, and for this line, it was on this side. And the overlap of all of those turned out to be this little region, and I've kind of consolidated matters here. Now, it turns out that in identifying a maximum or minimum value for z in this situation, that maximum or minimum value must occur at the vertices of the figure that we have before us. That is, the maximum or minimum values can only occur at that point, this point, this point, or this point, even though the constraints tell us that we are meeting all of the constraints for any xy pairs that are in this solution region. The maximum or minimum values, though, concerning those constraints occur only at vertices. All right, so here's what we have to do. We have to identify the coordinates of the vertices, and then we have to evaluate our objective function at those values. So we identify this vertex point at 0, 4, and this one at 0, 2, and this one at 3, 0, and this one at 5, 3. And then we evaluate the function for at all of those points, like this. Here's our objective function. And at the point 0, 2, z has a particular value. Well, we find it like this. If x is replaced with 0 and y is replaced with 2, then we have 3 times 2, 6 for the value of z. So z is 6 at the point 0, 2. At the point 0, 4, z has the value 12. At the point 3, 0, z has the value 12. At the point 5, 3, z has the value 29. So we look at this group of values that z has taken on at these vertex points, and it turns out that z is minimized at 6, maximized at 29. And actually, I shouldn't say z is minimized at 6. Actually, z is minimized at that point, and the value of z at that point is 6. And z has a maximum value of 29, and it takes on that value at the point 5, 3. So z is minimized at the point 0, 2 and maximized at the point 5, 3. Now in this next problem, as I read through this problem, try first to identify the objective function. What is the thing that we're trying to maximize or minimize, and see if you can write an equation for that. Try to do that much as I'm reading through this problem. A farming cooperative mixes 2 brands of cattle feed. Find the number of bags of each brand that should be mixed to produce a mixture having a minimum cost per bag, subject to the following constraints. Brand X costs $25 per bag and contains 2 units of nutritional element A, 2 units of element B, and 2 units of element C. Brand Y costs $20 per bag and contains 1 unit of nutritional element A, 9 units of element B, and 3 units of element C. the minimum requirements of nutrients A, B, and C are 12 units, 36 units, and 24 units respectively. Were you able to identify the objective function? Well, let's have a look at it, but first I'd like to organize the information a little bit. There's quite a bit of information here, and this kind of problem seems complicated because of that. So organizational skill is a really important aspect of success in this area. All right, we have two brands of feed, and we want to minimize the cost per bag. Now, minimizing the cost per bag, that is going to be the essential ingredient in our objective function. That is, our objective function is going to involve cost. And so we need to write an equation involving cost to get that objective function. All right, let's read through. For brand X, we had this information. The brand X costs $25 per bag, and it provides certain numbers of units of these nutritional values. So we have 2 units of item A, 2 of B, 2 of C, if you recall. And then we have a brand Y. In brand Y, each bag costs $20. But it provides 1 unit of item A, 9 of B, 3 of C. Now, we need at least, this is a very important idea right here, we need at least 12 units of item A, 36 units of B, 24 units of C. Now, with all of this information, we begin to build our objective function and our list of constraints. All right, the objective function is the first thing we concentrate on, and it's the cost idea. Now, the cost of the feed here is the cost for the number of bags of brand X and the number of bags of brand Y. Now, we're going to let X stand for the number of bags of brand X and Y stand for the number of bags of brand Y. And these guys cost $25 a piece, and those cost $20 a piece. So the total cost is just going to be X times 25, or 25X, plus 20 times Y. So let's go over here and we do that. We say, let's let X be the number of bags of brand X, Y be the number of bags of brand Y. So the cost equation, the objective function, is 25X plus 20Y. All right, now for the constraints. Now, the first 2 constraints are rather trivial. We can't have a negative number of bags of these things. So X and Y are greater than or equal to 0. So that's the first 2, those are the first 2 inequalities in our list of constraints. Now, the other inequalities are built on this idea. Let's slide back over this way. Notice we need at least 12 units of A. And we're told here that brand X supplies 2 units of A and brand Y supplies 1 unit of A. And we need at least 12 of them. Now, how can we represent the number of units of this nutritional item A that we have all totaled here for some unknown, some X number of bags of brand X and Y number of bags of brand Y? Well, if every bag provides 2 units, then 2X would be the number of units of A supplied by brand X. You see, so 2X. And then plus 1 unit of brand A is supplied by every bag of brand Y. So it'd be plus 1Y, you see. So it's 2X plus 1Y. 2X plus Y needs to be greater than or equal to 12. So we write that over here. 2X plus Y is greater than or equal to 12. And then we come back over here and build another one. And the next one is built by virtue of the idea that we need at least 36 units of B. Well, what it's provided from brand X and brand Y regarding this B idea, right up here. Brand X is supplying 2 units of B, and brand Y is supplying 9. So for every bag, for every X bag, we get 2 of these. For every Y bag, we get 9. So it's 2X plus 9Y needs to be at least greater than or equal to 36. So 2X plus 9Y is greater than or equal to 36. And we write that down over here. 2X plus 9Y is greater than or equal to 36. And in a similar way, we find the idea, the same notion for C. It was 2 units. You see, we are supplied 2 units for every bag of brand X and 3 units for every bag of brand Y. So it's 2X plus 3Y is greater than or equal to 24 because we need at least 24 units of that item C. Okay, so these are our constraints. Now, I have already drawn the graphs associated with these. Now these are just the x and y axes, that's no big deal, but these are lines, and these are those lines. Now I've left them sort of in a form like this, kind of in a raw form, because when you first draw these, they kind of look convoluted a little bit, and then you can clean things up quite a bit. Now first we need to identify which side of the line we're talking about, and that's pretty easy to do. If we looked at the list of inequalities and we use the origin as a test point, you know, x is 0, y is 0, then these two terms would go out. Is 0 greater than or equal to 12? No. And x and y would go out here. Is 0 greater than or equal to 36? Mm-mm. And in this one, 0 and 0. Is 0 greater than or equal to 24? No! Therefore, 0 is not a part of the solution region for any of these inequalities. The solution region is on the other side. The solution region is out here for all of them. Now, the solution region then for the entire situation is, let's see, we want above the x-axis to the right of the y-axis, and let's see, above this line to the right or above that one, and above this other one. And so the solution region is out here. It's all of this stuff. But we have to be above all of those lines at the same time. So this is the idea. We have to have all of this stuff going on. Here we go. All right. Now, to find the maximum or minimum value of something, we know we're looking at vertex points. And here we're trying to minimize cost. So we're looking to minimize something. And the minimization occurs at vertex points. This one, you see where the two lines intersect. And then where these two lines intersect is another vertex point. And then here's another one. Now let's identify those points. Well, let's see, I can clean it up quite a bit here by erasing a little bit in here. Okay, here we go. We've got a vertex point at let's see, this is 0, 12. We have another vertex point at 3, 6. We have another one at 9, 2. And another one at 18, 0. Okay, so that's our 4 vertex points. And so the minimum value, we minimize at one of those values. So we evaluate the objective function for each of these xy pairs. Let's do that over here. The objective function is cost is 25x plus 20y. So at 0, 12, we replace x with 0 and y with 12, and we find the cost to be $240. We do the same thing at all of these other values, and we find these cost figures. Now from the cost figures, if we want to minimize cost, we just take the smallest cost that we see over here. We see $195. And that minimum cost is achieved by purchasing or mixing 3 bags of brand X and 6 bags of brand Y. A company has budgeted a maximum of $600,000 for advertising a product nationally. Each minute of television time costs $60,000, and each one-page newspaper ad costs $15,000. Each television ad is expected to be viewed by 15 million viewers, and each newspaper ad is expected to be seen by 3 million readers. The company's market research department recommends that at most 90% of the advertising budget be spent on television ads. How should the advertising budget be spent to maximize the total audience? When problems seem this complicated, it's often very helpful to write an outline of the information and then kind of sort things out as you go through the outline. Here's an outline of the information in this problem. We were told that we have a maximum of $600,000 budgeted for this ad campaign, and we're given some advertising costs. TV time costs $60,000 per minute. Newspaper ads cost $15,000 per page. All right, now because we see the maximum idea here, words that kind of imply inequalities kind of tell us that we have a constraint going on here, and this information is going to be used in one of the constraints. Now, we're also told information about the viewers, and the viewer information will give us information for our objective function. Now, for viewers, we're told that for television, 15 million folks are going to watch each minute of advertising on television, and for newspaper ads, 3 million are going to watch per page. At most, 90% of the budget is to be spent on television, and we want to maximize the viewers. Well, it's actually, as soon as we hit this viewer information, we could have stopped right there and made our objective function. All we need is some kind of relationship having to do with TV time and newspaper pages. And so we need some kind of variable to stand in for the television minutes and the newspaper pages. Let's let X stand for the TV minutes and Y stand for the newspaper pages, and boom, we have our equation. Now remember, 15 million folks watch every minute of television ad time, and 3 million for each page of the newspaper. So if we let X be the number of TV minutes and Y the number of newspaper pages, then the viewers in millions would be 15X plus 3Y. All right, that's our objective function, and we want to maximize this. We want to maximize the number of viewers. All right, now we go fetch the information about constraints. Notice I've already written a couple of constraints here. X's and Y are greater than or equal to 0, because it doesn't make any sense for us to have negative values for TV time or number of pages of ad space in newspapers. Okay, at the very top we have a maximum of this amount is to be budgeted. Now, how do we figure the cost here? Well, the cost is $60,000 per minute of TV time, but those minutes are X values because we let X stand for the number of minutes of TV time. So it's 60,000 X, you see, and then the newspaper pages cost $15,000 a piece, so it's 15,000 Y. So 60,000 X plus 15,000 Y needs to be less than or equal to $600,000. because this is the maximum amount. We could spend less than that. So we have 60,000 X plus 15,000 Y is less than or equal to 600,000. Now I've gone ahead and simplified a bit by dividing through by 15,000, and it becomes 4X plus Y is less than or equal to 40. Then we come back over here and we look for more information having to do with constraints, something having to do with inequality. The only thing left over here in all this information turns out to be this business. At most, that's an inequality idea, at most 90% of the entire budget is to be spent on TV. Now we could calculate 90% of the entire budget. That's 90% of $600,000. That's $540,000. That's the most that we can spend on TV. How much are we spending on TV? Well, we're spending $60,000 per minute. The number of minutes is X. So 60,000 X is the amount spent on TV, and we want that amount to be at most 90% of $600,000. So we write that down. The TV expense, you see, is at most. That means less than or equal to 90% of the 600,000. Now that's 540,000 if we wanted to write it that way. And this is 60,000, and if I divide on both sides by 60,000, I find X to be less than or equal to 9. So these then are our constraints, and we want to put these on the graph and identify vertex points. But I think really that the hardest part of the problem has already been done. The interpretation of the verbal model into this mathematical form, I think, is the most challenging part of these problems. So organizational skills are really important in that part of the problem. Okay, let's go through and construct the graph. Now, these two constraints tell us we're in the first quadrant, and we write the equations related to these inequalities, and we get these graphs. Let's see, now this is the graph associated with the 4X plus Y is less than or equal to 40. So this is the line 4X plus Y is equal to 40. Notice on the Y-axis here, I've sort of consolidated matters because I don't have a 40 on here. I mean, I would have to go way off the board on the upside. So I've kind of consolidated things and letting each unit here be 5 units. So this is 5, 10, 15, 20, and so on. Now when you do that, it kind of throws things off in terms of the coordinates of points over here. When you read coordinates of points, you can't just be reading unit integer values. You have to think that every time you go up 1 unit, it's really 5. You see, you have to keep that in mind when you consolidate a graph like this. And by the way, and I should have mentioned this on the previous problem, but the easy way to construct graphs in this environment a lot of times is to just use x and y intercepts. Identify your intercepts, plot those 2 points, and then connect them with a line, and you're done. That's how I did this one. Okay, now we can use the origin as a test point if we want to, but the idea here with this graph is that we want below that graph. Okay, so we're below here. We're above the x-axis, to the right of the y-axis, below this line, and then the inequality associated with this x equals 9 was that x is less than or equal to 9, so we're on this side of that graph. So our constraints are met with values of x and y that are the points in this shaded region. Now we know that our maximization or minimization occurs at vertex points, and that would be this point, which is the point 9, 0, and at this point, which we don't know, and at this point, which is 0, 40. All right, what about this point that we don't know? How do we find that point? I've already mentioned that it's a little difficult sometimes to read coordinates when we've compressed one or the other axis. Well, we could take a guess, I suppose, but the best way to do it is to understand that these graphs are related to equations. And what we want here as a point that's on both graphs would be a solution to the system of these two equations. So we can take the equation associated with that line, the equation associated with this, which is simply x equals 9, and treat it like a little system of equations. So we would have these two equations. Now let's solve the system. Well, it's kind of trivial. We know that x is 9, so we just put an x value of 9 into this equation, and we find y to be 4. That means when x is 9, y is 4, so the point 9, 4 solves the system of equations, and therefore the coordinates of this point, 9, 4. All right, now we want to evaluate our objective function for the values given by the coordinates of these 3 points. And here's how that works. So the number of viewers is 15x plus 3y at the point 0, 40. 0 replaces x and 40 replaces y, so the number of viewers would be 120 million. And at 9, 4, the number of viewers is 147 million, and at 9, 0, 135 million. We want to maximize the number of viewers. The maximum number of viewers are, let's see, 147 million viewers are found at the point 9, 4. Now we need to interpret this though. What does 9, 4 mean? Well, 9 and 4, the XY pair, had to do with the number of minutes of TV ad time and the number of pages of newspaper ads. So we have 9 minutes of TV and 4 pages of newspaper ads. And another way to interpret it would be in terms of money. So we could either say, let's use 9 minutes of TV time and 4 pages of newspaper ads, or let's spend $540,000 on TV and $60,000 on newspaper, and we meet all of the constraints for this ad campaign.